Good afternoon, AP Physics students. This is your first flipped classroom video. So what we're going to do for this assignment is the following. Your homework will be to prepare the notes that go along with this video in whatever way that works for you. And as long as you are getting all of the key pieces of material that you need and have access to that during class, then we'll call it an okay set of notes. Now, I'm not just going to leave you at that. Tomorrow when you bring them in, I'm going to collect those. We're going to look through them and we're going to find the strategies that people are using that are making them particularly effective notes so we can share that information among us. This video is going to contain two parts. The first part is a quick review of slope-intercept form from your math class. This is going to be a foundational piece of math and graphical skill that we're going to apply to our data analysis. And then the second piece will be an introduction to some new material, not probably entirely completely new as you might have seen it in previous physics classes, but definitely something that's going to set you up for a successful run tomorrow at our first lab. So let's quickly go through a slope-intercept example in a couple different formats, and then we'll jump into the new material. So, don't forget too, the nice part about having a YouTube video is that you can click and pause at any time, replay different parts if you need to hear it again. Take advantage of that, and we will definitely catalog all these videos in a place where it's easy for you to access. So let's look at a slope-intercept problem as a form of review. And I've put a couple deliberate methods of talking about slope-intercept equations that follow slope-intercept form so that we can have a more well-rounded understanding of it. So let's start with just purely graphical representation of a linear equation, which is what slope-intercept form refers to. I have two different graphs here. I have one on the left. This is volume of a liquid, so we might say this is the volume of a sink as you leave the sink faucet running over time. Time here is on the x-axis, so you see a progression of 1, 2, 3, 4 seconds, and the volume is rising as that goes on. And then you see over here, similar graph. This time though, a couple different things to note. This doesn't have 0 as its y-axis, where it intercepts the y-axis. It actually has 1, and then as time goes on, you can see the progression of the volume in this one. So let's actually just take a second to look at each one individually in a couple ways, and then we'll do the comparison. So the first graph here on the left, one of the very first things I notice is that it is linear, and therefore should follow this form. And so just to review these pieces, the y here represents the y value at any point along this line. The m here represents the slope of this line. You've probably referred to that as rise over run. We're going to get away from that language because it's not very precise. We'll get into a much more descriptive language over time. X is the x variable at any point along this line, and then b represents the y-intercept. That is the point at which x equals 0. So x equals 0 right here at this point, so it's where is our y at that point. So given this, I can actually write an equation for this line with the information that's on here. So I'm going to do that. Remembering that this equation is telling us the y value for a certain x, I'm just going to leave y as it is. I need to put the slope for this particular line down, so I need to compute that. So I said rise over run a minute ago. Much more academic way of saying that would be delta y over delta x, which would equal the slope here. So the change in y over the change in x. So change in y would be this right here. So I can look at this one part of the slope and see the change in y here is 2 milliliters. And then I could look at delta x for that same time interval as 1 second, so it'd be 1 second. And so I get a slope of 2 milliliters per 1 second. I'm going to write that as a 2 in the equation. X is again the variable in the x direction for this equation. And we were talking about b here being 0. So the equation that describes this line is y equals 2x. Again, important to note here that the unit on this graph for the slope is relevant. It says 2 milliliters for every second, so it's telling us about a rate. A lot of times we will refer to the slope-intercept form in terms of physics, in terms of some rate of something happening. Let's see. So that is this graph. Let's go over to this graph and do the similar thing. So if you wanted to assess yourself right now, you could pause the video and try it out before I show you the answer. Good technique to get into the habit of. But of course I'm not going to wait for you to do that. Y equals mx plus b. Y for this is y. Let's find the slope of this one. So m equals delta y over delta x. So same, let's pick an interval over which to look. So here's delta y, here's delta x. So in this case, still delta x is 1 second, so let's make that 1 second. Delta y, in this case, we're going from 2 to 3, which is a difference, not of 3. It's a difference of, between 2 and 3, it's only a difference of 1 milliliter. And so that gives us 1 milliliter per second as a rate. Again, if this was a sink filling up, this would tell you how quickly that sink fills up over time. So this will be 1 times x plus, and in this case we do have a y-intercept. So if I look on my graph, where x is 0, y is equal to 1, and so the equation would be x plus 1. So let's compare these two very quickly, because there's some important takeaways to look at when you look at two different graphs and two different slopes. One is to recognize, just in casual language, this is steeper than this. You can compare those just visually to get that assessment, but we can be much more academic and much more specific if we say the slope of this one is greater than the slope of this one. This is 2 milliliters per second. This is 1 milliliter per second. So there's a concrete physical difference between what these graphs represent. And we want to make sure we understand that, because that tells us about something about how quickly, if this is a sink, how quickly it fills up. This one will clearly fill up quicker than this one over the course of time. So we can see that in the slopes just by comparing them. We can also see something else that's interesting, which we're going to call the initial condition. And the initial condition is, what is the state of this function when x equals 0? In other words, when there is no time. Where are we starting from? If x is 0 in this case, 0 times 2 is 0, so y equals 0 tells us that initially this sink had no water in it. In this case, if I plug in 0 for x to refer to the time when t equals 0, 1 times 0 is 0. I'm left with 1 though. This tells me that at the beginning this sink was filled with 1 milliliter of water. So there's a lot of information, physical information, to be gained from these equations, and to understand the relationship between the graph of that equation and the function that predicts it. So that's our quick review of slope-intercept form. It will be a relevant concept for us to talk about as we do our lab in the next couple days. Now onto some brand new physics material. This is your first real physics material for the year. So 3 ideas I'm going to lay out for you here, and we'll have a chance to practice them over the course of the next couple days. The first is the idea of position. Now, position is a word that's thrown around a lot by people who maybe are not physicists. It's a common everyday word. We're going to define it very specifically for our class. The position for an object might look something like this. I've drawn a number line here where I've identified a point I'm going to call 0, and then I've gone up from that 1, 2, 3, 4, and then I've gone down from that -1, -2, -3. The purpose of this number line is to define locations of objects, and this is how we get to a position, is by picking where an object might be located. Let's say the object is located right here at the 1. I would say that the location of this object is 1. Now I have to define a unit here. Let's go ahead and use the common physics unit of a meter. So this is 1 meter, 2 meter, 3 meter, 4 meter. I could say the location or the position of this object is equal to 1 meter. So position is the location of an object with respect to a defined coordinate system. This right here, you've referred to as a number line before. We're going to now call this a coordinate system. And I'm going to run out of space on my board. Nope, we're good. Coordinate system. And so you can't define a position unless you have something to reference it to. If you think about the football example, this is a perfect example. A football field has markings on the sideline. The purpose of those markings is to tell us where are the football players along the football field. That's how you find a position. Distance. Distance tells us the distance between 2 places that an object actually traveled. And so we're going to start with a very simple scenario. Let's say my object here starts at a position of x equals 1 meter, and a little bit later we find it to be, we'll call this x initial, x sub I. I'm going to use a subscript there to denote initial. And x sub f, or the final position of the object, was 3 meters. Well, in order for that object to travel that way, it had to go from 1 meter to 3 meters. And so I would get the distance of this object, or its length of travel, as 2 meters. Now, there are lots of ways, though, that that object could have made it from its original position to its final position. And so let's look at a different example. Let's say this was distance for the first object. So I'm going to write a 1 here for that path. Let's take a different path. Let's say this object started here, but went this way first towards the 0, and then stopped here, turned around, and went this way, and still ends up back at 3. So we're taking this path. We'll call this path 2. In this case, we'd say the distance traveled is still the total length that the object took. So, starting here, I go this way, that's 1 meter. Come back this way, that's 2 meters, and then continue the rest of the distance. That adds up to a total of 4 meters. And so in that case, the distance would be 4 meters. So distance, you have to take into account the entire path of travel. Last term, displacement. This is the one that's probably most new for you. Displacement is a value that's calculated as follows. Delta x equals xf minus xi. So delta x equals xf minus xi. What is this saying? This says delta, or we'll read this as the change in x. So how did x change? Well, to find that out, you just take xf minus xi. So let's do that for this scenario. Delta x equals 3 minus 1. So delta x will equal 2, and I want to make sure I have a unit on there, meters. So it's 2 meters. Well, what does that mean? The way you know that you're talking about a difference between distance and displacement is as follows. Distances track the entire path that was traveled. But all a displacement tells you is how far apart your initial and final points are. So it's just the distance between the two. It doesn't matter what path you took to get there, it just matters what that original distance was. So you could say, I have a starting point and an ending point. There are lots of paths you could take to close the gap between those two. So you could take any one of those 3 paths to get from point A to point B, point A, point B, and all 3 of those distances would be different, but the displacement for that object between A and B would be the same no matter what, because their initial and final positions are the same. So, that is a new concept for you guys to wrestle with a little bit. Hopefully you have a good chance to get your notes down, but also put some questions down that you might have, because as we talk about this in context of an experiment over the next couple days, there'll be a good opportunity for you to wrestle with some of these ideas so you can better your own understanding. As always, if you have any questions after this, you're welcome to text or call me, but if not, we'll see you tomorrow.